All right, this last topic for this chapter is on redox reactions, and we're going to do half of it today and half tomorrow. This is a new kind of reaction that you did not do in honors chemistry, and it's actually one of the most important kinds of reactions that you do in your life. This happens in batteries, it happens in your car engine, it happens all the time in different places. So you're going to see a lot of redox reactions throughout this chapter. Two things are actually happening in a redox reaction. One is called reduction and the other is called oxidation, and they just combine those two to call that a redox. You cannot have one without the other. So first of all, you have to have reduction and oxidation happening at the same time. You can't just lose electrons and not gain them somewhere else. So first of all, it's the whole idea is that you're transferring electrons. Something is going to lose electrons to become positive, and that's called oxidation. Something else is going to gain electrons, which makes it more negative, and that's called reduction. So the oxidation is going to become more positive, and reduction is going to become more negative. The reduction makes sense because you're going down in charge, it's becoming more negative, so you're reducing it. That's how I remember it. Oxidation, you just have to remember. And there's a lot of little sayings that you'll hear people say. One is Leo the lion goes grr. So Leo goes grr, lose electrons, oxidation, gain electrons, reduction. So that's kind of how you can think of it in your head. I think the guy on Crash Course says oil rig. So oxidation is losing and reduction is gaining. Either way, you want to remember, it doesn't matter. You just have to remember that when you're losing electrons, it's called oxidation and gaining is called reduction. And again, the number of electrons lost has to equal the number gained. You can't just have oxidation by itself without having reduction. Sometimes we write them as half reactions, but it's not a real reaction, it's a half reaction, because again, you have to have both of them. I'm going to keep on saying that because that's a common AP question as well. These are some examples. I told you combustion of fuels like in your car engine, all kinds of batteries, photosynthesis is a redox reaction, so this happens all the time in your life. Before we can do a redox reaction, though, you have to understand how to label oxidation numbers. And you kind of learned this in honors chemistry, where you put, like, on top of the alkali metals, you put a +1, on top of the alkaline earth metals, you put a +2. That's kind of a guide to go by, but it's not set in stone. That's the first thing you have to get into your head, is that everything you learned in honors chemistry does not necessarily apply. We kind of teach it as black and white in honors chemistry, and you're going to learn in AP chemistry that there's actually a lot more gray area, and it's that gray area that is tough, which is why we save it for AP chemistry. So first of all, most things that are close to the edge of the periodic table keep the oxidation number you would think they are. So alkali metals are probably going to be +1. Halogens are probably going to be -1. But as you get closer to the middle of the periodic table, they don't always keep their oxidation numbers. So for example, nitrogen is -3, what you learned in honors chemistry. Sometimes it actually goes +5, and sometimes it can be some other random numbers. So it's not always going to be what it has on the periodic table. All right, let's go through some of these rules. That first rule is a really tough one. If you have a pure element all by itself with no charge on it, the oxidation number is actually 0. If it's going to have the charge that it normally becomes, either it will show the charge or it will be bonded to something. So if I had something like sodium sulfate like this, in this case, sodium does have a +1 charge. I don't write it because it's in the compound, but it does have a +1 charge. But if I just said, what is the oxidation number of plain old sodium all by itself, it's actually 0. It has not lost its electron, and that is why pure sodium is so dangerous. You may have heard that if you drop sodium into water, it explodes, and that's true. We used to be able to do that for you as a demonstration, and now our county said it's too dangerous, so we're not allowed to show you that anymore, but you can find videos of it on YouTube. Just check out sodium in water, and you'll see people exploding water all over the place. The reason why it's so dangerous is because sodium all by itself has a neutral charge, and it really, really wants to get rid of that one electron. It's extremely unstable to have that one valence electron. Once it loses that one, the next shell has all 8, and it meets the octet rule and makes it very stable. So sodium is going to do that very fast and very violently, and that's why it's so reactive. But once it becomes sodium plus, once it loses that electron, then it's stable. And that's the sodium that you're eating in your food. When you eat table salt as sodium chloride, it's safe enough to eat. It's not going to explode your stomach. So the first thing to recognize is that if you have a plain old element all by itself, it's going to have a zero charge, a neutral charge. If it's just a regular thing with a charge on it, you use the charge that it has. So if I tell you that it has a +1 charge, use that as its oxidation number. Oxygen is almost always -2. That's a good one to know. There is an exception there. And this was actually on the AP exam last year. The only peroxide I've ever seen them ask about is hydrogen peroxide, but that's a good one to go ahead and understand. Hydrogen peroxide is H2O2, and this is the case where oxygen is going to have a charge of -1. So that's just an exception that's good to know. Hydrogen is almost always +1 unless it's with a metal. And fluorine is almost always -1, and you're going to add them all up to be 0. So we're going to do a few examples, and I'll show you what I mean by all this. And actually, let's just do an example. Let's do KMNO4. So what you're going to have to do is assign oxidation numbers to each individual element. I want you to start with oxygen or hydrogen if you have them. Oxygen you can assign as -2 unless it's hydrogen peroxide. Oxygen or hydrogen you can assign as a +1 unless it's with the metal. And then do everything else based on those. So in this case, we're going to say oxygen is -2, and you're going to assign it per atom. So I'm not going to say that oxygen is -8, even though I have 4 of them. I'm going to say it's -2 because we're talking about per atom. So each oxygen atom is going to be -2. And then we can go ahead and do K is probably going to be +1. It's on the edge of the periodic table. It's an alkali metal, so it's pretty certain that's going to be +1. So now you can see that you've got +1 here. -2 times 4 is -8. And the point is that all of these have to add up to 0. So now you can see that Mn is going to have to be +7, so that +7 and +1 is +8, and that will balance out to the -8. So it's kind of like a logic puzzle. I think they're kind of fun. It's kind of like, if you like Sudoku or any of those number puzzles, it's kind of like that. You just have to figure out what they would have to be to add up to be that, to be 0. Let's do another one. Let's say we have aluminum nitrate. For this one, since we have a polyatomic ion, I know that within the parentheses, the charge on NO3 is -1. So I can figure out what the N and the O would have to be to make that equal -1. So oxygen is -2, and we have 3 of them, so that's going to be -6. So nitrogen has to be +5 in order to make NO3 equal -1. I know you're probably like, what in the world did she just say? Let me say that all one more time. So oxygen we know is probably -2. And we have 3 of them, which makes it -6. I'm only doing what's inside the parentheses. And I know that nitrate is a polyatomic ion with an overall charge of -1. And so if oxygen is -6, then nitrogen would have to be +5 to make the overall charge -1. And now I know that nitrate together is -1. I have 3 nitrates, which makes that -3. And so aluminum would be +3. And the answer that you're writing is per atom. So the answer for this one would be +3, +5, and -2. The answer for KMNO4 would have been +1, +7, -2. If you have a polyatomic ion, you can make them add up to that charge. So if we're going to do the charges for sulfate, the oxidation numbers for the elements in sulfate, instead of making them add up to 0, I need to make them add up to -2. So we can assume oxygen is probably -2. Times 4 is -8. And I need them to equal -2. So in this case, sulfur is going to have to be 6. So again, it's kind of an algebra problem. Sometimes you can get numbers that don't equal a whole number. So in this case, Fe3O4, if you have 3 irons and 4 oxygens, each one is probably -2, and we need it to be 0, you would get 3x equals 8. So x equals 8/3. And you're like, wait a minute, how can a charge be 8/3? And that's because not every iron has the same charge. So some of the iron in that compound has a charge of +3, and some of it has a charge of +2. So just be aware that you can get a fraction as an answer. We talked about oxidation and reduction. Oxidizing is one element that's losing electrons and the charge goes up. That's what letter B means, is that it becomes more positive. And then the reduced thing goes down. So let's look at this example here. First thing is you want to assign oxidation numbers. Oxygen is probably -2 times 4 is -8. So the nitrogen needs to balance that out by equaling +8. And I've got 2 atoms, so each one is going to be +4. Now let's go over here to this one. Hydrogen is probably +1 because it's not with a metal. Times 4 is 4. So nitrogen is going to need to balance that out and be a -2. And I told you, watch out for nitrogen and phosphorus. They tend to change their oxidation numbers quite a bit. Over here, this oxidation number is 0. And I didn't mention that, but in this case over here, when we said sodium was 0, it also applies to the Hofbrinkel elements when they're by themselves. Any of those like O2, Cl2, those are all going to be 0 when they're by themselves. And then water, we have -2 for oxygen and +1 for hydrogen. So now let's look and see what has changed. I see that this nitrogen went from +4 down to 0. So it got reduced because it went down in charge. Oxygen stayed the same, -2, -2 on both sides. Hydrogen stayed the same, +1, +1, but this nitrogen went from -2 up to 0. So that one was oxidized. So in this case, the nitrogen got reduced and oxidized. And that is what a disproportionation reaction is when the same element gets both oxidized and reduced. Half reactions is when you're going to pull out just half of either just the oxidation or just the reduction. So for example, let's do an example of this. If we wanted to do iron plus zinc with a 2+ charge yields Fe with a 2+ charge and zinc neutral. And the question says to balance this with the half reaction method. So first I'm going to pull out iron and just balance iron. And now the number of atoms are balanced, but what we're trying to balance here is the electrons. And first of all, you're always going to put the electrons on the side with the higher charge because electrons bring the charge down. So these two, we have iron neutral versus iron 2+. So we're going to put electrons on this side. And we need 2 electrons, 1 for each iron. I'm sorry, 2 for each iron because it goes from 0 to +2. So this is the half reaction for the oxidation because iron is losing electrons. Then we can do the same thing for zinc. So here's zinc with a 2+ charge going down to 0. Again, always put the electrons on the side with the higher charge. And we need 2 electrons because it's going from +2 down to 0. This is the reduction half reaction because zinc went from 2 down to 0. It got reduced. These are the 2 half reactions. Then we can put them back together. And in this case, they're all going to cancel out. So the electrons, we have 2 on this side and 2 on this side. And so when we put them back together, we're just going to get the original reaction back again. But you won't always. So sometimes when you balance it, you're going to get different numbers. And I'll go through some more of these with you during our live sessions as well. And it's just a list of the metal strengths. So a lot of times when you're doing single replacement reactions, there are always going to be redox reactions. So sometimes you need these. This is the activity series. And you can figure out which ones are good reducers and good oxidizers. And we're going to save 410 for tomorrow. So that's about it. But if you're having trouble with some of these, just come to our live session and we'll go through a whole bunch of these together during class. And I'll give you some more details about them.